shows here. So in the chemical model, okay. So in the chemical model, especially for the model 98 and 99, sometimes we call this the MQM model 99 and 98 as, I'm sorry, there's also as a grand unified thermodynamic model. So it's a grand unified, it means we can combine the different kinds of thermodynamic model under this umbrella. That's why we call it sometimes GUT, GUT model. And because we can also reduce this model down to the random mixing model. I'm sorry, this is not very good English. I'm sorry, I just write in the morning and I didn't check. Okay, so that is within this model number 98 or 99, one sublattice random mixing model can be realized as it is in the model number 1. Okay, so we can actually reduce the model 98 down to the model number 1 with respecting actually the Z coordination number. Because in the chemical model, you have to assign the coordination number already. Okay, so I think you remember this equation. So when you have binary system, random mixing model with the coordination number, you can have this kind of expression for the binary Gibbs energy. So G of solution is the mole fraction of A, G of A pure Gibbs energy, and mole fraction of B Gibbs energy plus mole fraction of B times Gibbs energy of B pure plus random mixing model and A and B. And then you have typically Z with AB parameter XA, XB. So this is the one I introduced in the very first time here. So this one. So we can explain in this way. If you assume the GAB is the model parameter, okay? Is okay? Now, in the chemical model, we typically define the Gibbs energy in this form, yeah? In chemical equation in this form. So AA plus BB become 2 moles of AB. So this is chemical expression. And so because this model 98 is still chemical model, so we want to use this delta G as a model parameter. But when you actually make this delta G as a model parameter, we can sometimes set this one as a real chemical model, which can change actually your entropy, or we can set this one, this value, but we can still assume the random mixing. So we can use this one, assume the random mixing this way. Okay? But when you look at actually random mixing model, so for example, let's go back here. So when I actually introduce this model here, so this is chemical solution model I explained on Monday, assuming random distribution of A and B. At that time, I say that this energy here, so this energy, and with the Avogadro number, so this whole energy was kind of the omega parameter. And this one is the 1 mole of AB from half mole of AA and half mole of BB. Is okay? So that's actually the inside of random mixing parameter in the model number 1. Okay? So now, if you look at the chemical equation, we typically express chemical equation in this way. So it means we are respecting 2 moles of AB for this delta G reaction. Okay? So we have to divide this one by half first. So half of the AA plus half of BB plus become 1 mole of AB, then it means this energy become half of the delta G AB. And this is same as basically the omega parameter in the regular solution. Okay. Of course, in the previous slide, in the omega, I even put the Z parameter inside, but forget about Z at the moment. So coordination at the moment. So if you are assuming the coordination is number 1, this is basically the omega regular solution parameter is same as the half of the delta G AB. Okay. So now, so this omega here is replaced by the half of the AB. And then we have to multiply the Z value here. Okay. So now let's assume this one. So now let's assume we have the model parameter L, because why I actually show you L here is typically if you are using the Ledley-Kist model, the Ledley-Kist polynomial model, then the parameter is L, L0, L1, L2, and etc. So I just show you as L as a model parameter in the random mixing model. and then without the definition of the coordination number, it means Z was 1 in the random mixing model typically. Okay, and a lot of people actually, when they actually use this kind of random mixing model, they don't care about the Z, so they just assume that Z equal to 1, and then they optimize the parameter L, okay, to reproduce all the Gibbs energy. Okay, so this one, and then so now if you assume this one L, so whole this value should be L in the typical model number 1. Assuming there's no Z, it means assuming Z was 1. Okay, and then we want to actually put that parameter, that L parameter, into this kind of expression in the model 98, assuming some Z value. So, for example, in the magnesium and the tin example we did last Monday, on the Monday, Z was the 6. Do you remember that? So in order to actually assign the 6, we have to actually change this GAB parameter from the L value by assuming this Z and half more over this one simultaneously. So when you have the L parameter, assuming it's a random mixing model without, typically saying about Z, it means Z equal to 1. So when you have L parameter from literature, then you have to change this L equal to as half more of Z, so half times Z times delta GAB equal to same as L. Okay, then this delta GAB equal to L times 2 divided by Z. Okay, so this is the trick we have to use in the chemical model. So let's assume somebody did magnesium tin binary system by using the regular solution model or random mixing model. They have L parameter. Okay, how can I enter this L parameter into my chemical model, assuming the end member of the magnesium and silicon end member Z equal to 6. Okay, then I have to use the Z equal to 6 here, and then I have to take their L parameter as it is, or multiply by 2 divided by Z. That's actually delta GAB you have to enter into your chemical model. So I'll explain this one a little bit later again, okay, with the real actual example, okay. So then how we actually enter that, how we assign in the MQM model, the model 98, this is the random mixing parameter. This is random mixing assumption, okay. So when you actually select the parameter here, so you can select, okay, so when you actually take the two components, two species, and then when you actually click, mouse right click, you can have option like this. And then in the option, in the last week, we took this add a pair fraction expression. Okay, this is the chemical, and this is also chemical. Okay, these two is chemical expression. But if you take the very first one, Gregor-Williams, as soon as you click this one, FactSage understand that this binary is the random mixing model. Okay, even though you are using model 98 as umbrella, but whenever you select your parameter, interaction parameter, when you select this Gregor-Williams expression, then FactSage assume that this is the random mixing model inside of the chemical model. Okay, so that's how does it actually how does it done inside of this model. Okay, so when you do that, you can take, for example, Ledderchest model. Then if you click it, you can have this kind of expression coming out, and then you can assign the L value. Okay, then it'll actually, you can realize it actually that random mixing model inside of the MQM model 98 and 99. Okay, so let's try to actually do this one today. Okay, now stop sharing. Now I'm going to share entire my screen. Okay. So now let's go to the FactSage. So in the FactSage, I'm clicking the solution file. This is the solution. Okay. So I already have magnesium, tin, and silicon as one of the species A here. Okay. So when you have when you make model 98, so this is model 98, two sublattice chemical model. But if and then we have the A site and the B site that I explained last time. In the A site, you can do the mouse right click and you can add the species. And I already have 3 species: magnesium, tin, and silicon. Okay. And in the B site, you can add 1 species, and then I have vacancy. So B is not, there's no mixing in the B. So basically, even though this is 2 sublattice, but the entropy is same as the 1 sublattice model. Okay. So eventually this is same as the 1 sublattice chemical model. Okay. So these 3 is the species. Okay. Now you have to assign the end member of each one, and when you actually make end member, you have to click this one of species from A side, one of species from the B side, and when you do the right click, you can add end member. Yeah. So we did that. So each one, magnesium, tin, and silicon. Okay. And because all this one is liquid, so we just assign the liquid Gibbs energy from the function we define above here. Sorry, from the function we define above here. So for example, silicon liquid. Yeah. So all this one is done. Okay. Now, what I want to do is now I want to add interaction parameter between each binary system. Then what you have to do is you have to click this one, and then this one, and for example, this one. So 2 species from the same sublet A side, and then vacancy from the B side. And then you do the mouse right click, then you can add, okay, Bragg-Williams term, or chemical term, or pair expression term. Okay, so you can enter one of these. And so as I mentioned, if you are taking these 2, one of this one, either of this one, it will assume that this is real chemical model. But the expression of the access parameter will be different. And this is going to the equivalent fraction expression, and which we are not using anymore. And this is the pair fraction expression. Pair fraction expression. So this is what we are typically using in this day. Okay. And then now, if you go to the, for example, tin and the silicon. So tin and the silicon. So, I'm sorry. Tin and silicon and the vacancy. And if you are taking this one, I want to use the Bragg-Williams term, the register. Okay. So let me show you my paper again. So let's look at where actually that information is available in the paper. So if you go down, so this was the parameter, okay? So here, magnesium tin binary. So this one, like this, and the tin silicon binary looks like different, yeah? You have L parameter instead of the delta G parameter, okay? And so there's something different. So what's the difference? If you look at here, so this is the description of the model. So whenever you actually look at whenever you find actually the paper about thermodynamic assessment paper like this, you have to look at the model always. Otherwise, sometimes you make a mistake when you actually take the parameter directly from the table, because sometimes people using different sign, plus sign to the minus sign, okay? And so you have to go back to the actually your expression, the model, and then look at it a little bit more carefully. So this liquid model, I say we are using the modified chemical model here. And then, so this was good, and then we say all the things, and then etc. and etc. And then, but if you go down further, okay, for the binary tin silicon liquid solution, the short range ordering is negligible. So it means there's almost no short range, which means it's a very random mixing solution. So this liquid shows slightly positive deviation from even ideal behavior, ideal solution. Thus, the random mixing approximation of the molar Gibbs energy can be still used. And so this is the expression we are using for the binary tin and the silicon. So if you look at this one, okay, so this is exactly the same as the Gibbs energy of the pure tin and the pure silicon, and random mixing, the computation entropy here, and then TXS parameter. Okay, and this is exactly the same as model number 1. And then that access parameter is typically given by this one. This is L type of the parameter, Redl-Kipster type. So power 1 is automatically, kind of multiplied, and then you have L parameter here. with the power n. Okay, so this is Redlich type of the actually the model parameter. So, and then those parameter is this one. Okay. So how can I enter this one? Then you have to basically go to clip here. So let me show you one by one. So this L0 parameter, silicon and tin. So you have to say tin, silicon, vacancy, and the mouse right click, and then add this Bragg-Williams GXS parameter, Redlich-Hister. I'm sorry, GXS parameter, Redlich-Hister. If you click it, you'll say that, okay, so this one AB, A equal to tin, B equal to silicon. So you have to be little bit careful here. Silicon and the tin, and this is tin and silicon, yeah? So when you actually have the odd, so even number parameter, there's no problem, but odd the number of the parameter power, you have to be little bit careful because of this sign here, okay? So when you have, so L0, so basically what you have to enter is this, and then, as I told you, and then, so we have to enter this one, but we have to respect that this chemical model have the coordination number. So that coordination number was defined here, yeah? So tin, coordination number 6. Silicon, coordination number 6. So we enter this one as a by default value, yeah? In the liquid actually the metal. So now, when you enter this parameter then, so what you have to do is L0, but this L0 parameter, original value is this one, but when you enter the L0 parameter inside of the backstage, you have to now use this expression. So L0 times 2 divided by Z. It should be entered as L0 in the chemical model. Okay, do you get it? So now, so let's go back here. So what's the L0? So this value, 25364.6, and then I'm dividing that, I multiply that by 2 divided by 6. Okay, and then this value, 8454.867. So this value should be entered here. Okay, and that's already actually done. So let me show you that. So here, L0, so 8454, blah, blah, blah. So L0 parameter. Now L1 parameter, similarly, so L1 was 3148.8, and so I have to divide this one by basically 3, so multiply by 2 divided by 6, so it's divided by 3, then it's 10,049.6, but why this is minus instead of the plus compared to here is because this order is A equal to tin and B equal to silicon. Tin minus silicon, power 1. But however, this order is the silicon minus tin, power 1. So we have to flip it. So that's why we have to change the sign for the L1 parameter. So it's minus instead of plus. Okay? And then L2 parameter is same. So L2 parameter 1486.967. Same thing. If you go here, this divided by 3, then you'll have this value. Okay? So this is how we enter it. Okay? So when you enter the regular solution parameter or the random mixing model parameter in the chemical model, you have to respect your Z value again. And how we actually do that is you have to divide by your L value, multiply your L value by 2 and divide by Z value. Then that's actually the value you have to enter in the chemical model. Okay? That's good. And then let's go back again because some of you probably still have a little bit confusion. So let's look at this magnesium silicon parameter here. So now this is MQM model as it is. It's original MQM. So what you have to do is magnesium and the silicon and then vacancy. And you have to push the control key down all the time. And then do the mouse right click. And then now you have to enter your chemical parameter, but as a pair fraction expression, okay, and GE, and the very first one, 0, 0 parameter is this one. So minus 2647 4.8. Yeah. And then you have to enter the another one. Go up to the mouse right click. Again, this one, second parameter. I'm sorry, I had a mistake. So here, and then there's template dependence term here. So minus 9.8335 times T. Okay. And then second parameter is now 2, 0. So magnesium power 2, silicon power 0. So magnesium A power 2 and silicon power 1, power 0. So it's 2, 0. Okay. And then this is 1882.8. And then third one, I have to enter one more. So to the mouse right click. Then I'm adding one more access parameter. And this is 0, 1. So 0 and the power 1. So silicon is power 1. And then this is minus 8819.286. Okay. So it's done. So I have magnesium tin parameter and the silicon tin parameter. And then, sorry, I'll explain this one again. And then all this one is zeros. And then magnesium silicon parameter. Okay. So all this binary model parameters already entered into my solution file, in the ternary solution. Then what you have to also look at is how to, so when you have any ternary system in the backstage, actually solution database, you have to assign what kind of interpolation technique you want to use. Okay. So this is the one last step you have to do. Okay. So now if you, so I didn't actually specify, sometimes I specify here, say, okay, what kind of interpolation technique we are using, or sometimes you have to actually go to the little bit detail in this, inside of this model description, and then you can find the information. So for example, in this case, so look at this one. So as I mentioned above, the binary magnesium tin and magnesium silicon liquid show strong ordering. So that's why we use chemical model. It has a very negative interaction between magnesium tin and magnesium silicon. But the binary silicon tin liquid shows slightly positive deviation from the ideal solution. Thus, the thermodynamic property of the liquid solution was calculated from the binary and the ternary parameter using asymmetric tube-like interpolation technique, assuming magnesium as asymmetric component. Okay, this is something you have to keep in mind. So what that means is like this. So I mentioned that we can use the so-called interpolation technique. So this is magnesium, okay, and you have tin, and you have silicon, okay. So I have to make a prediction of my ternary Gibbs energy for liquid solution from the binary liquid solution parameter, okay. So there's many interpolation techniques to make a prediction, but I'm assuming that the magnesium is different from the other two because this is negative interaction. This between these two is negative interaction. This is slightly positive interaction even, yeah. So these two binary is different from this binary. So that means if you look at actually this one is different from the other two. Magnesium is different from the other two. Okay. So typically in this case we are using tube interpolation technique like this. So the parameter in the Gibbs energy of this one is predicted from the parameter here, Gibbs energy here, and Gibbs energy here, and the Gibbs energy over there here. Okay. So this is the two parameters. So in the fact stage, when you select actually now the interpolation technique, it is very easy actually to do it because it shows as a graphic form. So let's look at it now. So in the fact stage, now how to add actually interpolation technique. Okay. So now we have to select 1, 2, 3, all of them with a vacancy because it's ternary kind of, kind of the parameter. So all three, and then to the mouse right click, then it will say, okay, edit ternary interpolation. Okay, edit ternary interpolation. So if you click this one, now it shows that, okay, what kind of interpolation technique you want to do. Okay, so for example, this is magnesium, tin, and silicon. That's exactly the same figure as I showed you before. And then this, so I want to predict this one from binary to the from each binary. So this side, so if you are using this one, it's 무제한. Can you see it? So it's like a rectangular kind of interpolation technique here, from this point here, rectangular. And this is 무제한. And so we don't want to use this one. And this is color. We don't like to do this one. Color means I'm drawing straight line from this corner through this one and then connecting to this point. Okay, that point is color. And this is the tube, but this tube is actually parallel to this amount of tube. But I need actually magnesium is the parallel in this tube. So same amount of the magnesium point. Same amount of the magnesium point. Tube, and this side is color because we are taking this one all the way down to this one. Because these two is symmetric kind of thing. This is asymmetric. So this is the interpolation technique we have to assign. Okay? If you don't assign the interpolation technique, PacSage assume by default, PacSage in the chemical model or model number one, if you don't assign any actually the interpolation technique, PacSage assume color type of interpolation technique automatically. So that's actually here. I mean, I didn't explain this one, but that's here. So chemical group number one. Chemical group number one. Chemical group number one. So you can actually change group number two too, but chemical number one, it means all these three is in the same group, and it means all this one behave similarly. So we assume that all this one is the same kind of the component in the solution. So symmetric component. Then if you don't assign this kind of interpolation technique, it will assume basically this is color, this is color, this is color automatically. Okay? But in this case, we have to change that because this is not anymore symmetric. This is asymmetric. So we have to do it in this way by overwriting actually this editing, this ternary interpolation. Okay? That's why you say editing. Okay? And then you can add also access parameter. Okay? So now let's go back again. There's actually one more thing. Where's my, yeah, okay. So now there's so if you look at this one, okay, this is the ternary actually the parameter. So then Gibbs energy GAB is the forming in this way, blah, blah, blah. And this is interpolation technique. And then here in the bottom, and then blah blah delta GAB is interpolated and etc. And then this one are ternary additional model parameter to adjust the actual Gibbs energy of the ternary system from the prediction. Okay, so we made the prediction, but however sometimes that prediction is not enough. Then we have to make some additional correction inside of ternary system by adding some additional parameter. So that's actually ternary model parameter. In this case, the ternary model parameter is defined here. So ternary model parameter Q, Mg, silic, Mg, tin, and then actually the open bracket and then silicon inside the bracket, and then magnesium, silicon, and bracket and tin, and etc. And power 0, 0, 1. So how to enter this one? So if you go there, now. So I have magnesium, tin, silicon. Because it's ternary parameter, you have to select all of them. And then do the mouse right click. So this was the binary parameter, or this was the parameter we used. And now we can actually go to this pair fraction expression again. And then if you click this one, now you can actually have the ternary parameter because we select all the three. So if you click this one, it will say that, okay, now you want to use the G access for ternary parameter. And then you don't have to worry about this part. This is basically same as the expression you are seeing in this actually the equation here. So in this equation, okay? And this is actually automatically changing depending on how you set actually your integration technique. Okay, so you don't have to worry about it. And then now go back to this expression again. The only thing you have to do is like this. So okay, so this one A, B, C, and C is actually in the inside of inside of actually this parentheses, yeah. So A, B, C. So A, B equal to magnesium, tin, and then C is silicon. So magnesium, tin, and then silicon. Okay, so this is corresponding to this one. And then 0, magnesium is A equal to magnesium, B is tin, 0, power 0, power 0, and then last one, power 1. And if you like power 2, power 3, power 1, and then if you like this one also power 1, 2, 3, you can change it in this way. So 0, 0, 1, magnesium, tin, silicon. So this is exactly the same as this one. That's good. So the parameter should be 10 minus 4, 6, 0, 2.4. Is it okay? You can enter it this way. And then we have one more actually tunnel parameter we need. So go again to the same thing and then add additional parameter. So this one, second one. And now this is magnesium, silicon, and tin. So magnesium, silicon, and the tin, yeah. Okay. So now if you click this, this C, look at this one. A, B, C, but only on the C you have the black dot. And the other two is the open actually dot. Okay. So when you click this one, you are changing the sequence. So when you take the B, so B is inside the parentheses. Is it okay? And then when you take A is inside of the parentheses. Okay? So this is how we change the coordination of A, B, C in the parameter. Okay? So we need A, B, and C should be, the thing inside of the parentheses should be tin. So that's actually tin. Okay? So this is the parameter we have to use. Is it okay? A, B, C or C, A, B is same. CA, the sequence, it doesn't matter because it's the same. 0, 0, we just use 0, 0, then it's okay. So 0, 0, and then power 1, and this is minus 4, 6, 0, 2.4. Okay? So then, you may just what's the meaning of this one, really? The meaning is, so we know there was the interaction parameter between C and A, yeah? In the binary AC system, we have the interaction parameter C and A, okay? That interaction parameter is influenced by the B component. That's what it means. So this parameter means C and A interaction parameter, or A and the C interaction parameter from the binary. When it's going to the ternary system, that's influenced by the amount of the B by this factor. And by using this equation with this factor, is actually the additional actual parameter. Okay? And this one is AB. So AB means magnesium and tin interaction parameter is influenced by the addition of the silicon by this additional amount. That's what it means. Okay? So you can use as many ternary parameters, as possible. But typically, if you are doing the Gauss thermodynamic modeling from the binary, and then when you go to ternary, you need very few parameters to fix it, to fix this kind of ternary system. But if you are using, instead of the MQM parameter, if you are using MQM model, if you are using the random mixing model, you may need about 10 different parameters to fix everywhere. So it's much worse than actually this case. Okay? So that's good. And the only thing I actually forgot was the coordination number and magnesium and silicon. So magnesium silicon is chemical model. So we define the coordination number of the pure magnesium, pure tin. And however, in the binary system, we can also change the coordination number again in the liquid phase. Yeah, that's what I actually explained last time. So magnesium and tin. So for example, here, magnesium tin in the binary system, we change the coordination 3, 6. Yeah. So we need a similar thing. Magnesium, silicon, vacancy, to the mouse right click, and speed, and then this mixing also overwrite this one, Z in the binary system, and then this one, silicon, so magnesium is 3 and silicon 6 again. Okay, so this one you have to enter to make actually your magnesium silicon actually working again. Okay, so then let's look at actually some of the actually this result here. So this is phase diagram for the magnesium and tin binary system. We have Mg2Sn, so it means I told you in the liquid phase you have short range ordering here, Mg2Sn actually composition. So that's why we use the magnesium actually combination number as 3 and tin as 6 to reproduce my short range ordering here. Okay. And similarly, if you go to the magnesium and silicon, you have similar result. Magnesium and silicon, sorry, one page up. So magnesium silicon, you see there's actually the compound here, and so we can expect more or less short range ordering here too. Okay, and that's also shown in the your Gibbs energy function and the enthalpy function. So look at this. You have the minimum around this composition here. Okay, so that's how typically we are setting the binary coordination parameter. So we are overwriting our default 6 and 6 into the 3 and 6 or 6 and 3, depending on the composition. Sometimes you can use the 4 and 6, or sometimes you can just allow as it is as 6 and 6, or sometimes you need a very weird parameter, 2 and 8. So for example, it's a very strange system, but that's actually because of the size of the actually atom in the liquid phase is different. So for example, if you have the big atoms, so let's just you have football, and you have the football actually ball, and then you have the baseball ball. So baseball is much smaller, yeah. So football, the ball from the football actually ball from soccer. Soccer should be I'm sorry for the French people here. Soccer. The ball. I don't know. So when you have the big ball, the jet around it is much bigger than smaller. Okay. So depending on the atomic size or cationic size of the species in the liquid phase, the coordination number could be changed. Very much in the binary system. Okay. So that's one of the physical reasons why we have different kinds of the jet could be formed in each binary system. Could be different. Should be defined in each binary system. Okay. But anyway, we can do it in this way. And then we can actually do if you want to, you can draw some diagram. And before actually I go to the equilibrium program and the phase diagram program to show you to demonstrate how to do those kind of calculation. Let me show you one last thing. So this is what you need also for your homework number 2. So I ask you to make this alpha magnesium solution as well, yeah, from the parameter here. Okay, and probably some of you actually figured out how to do it, and some of you have some difficulty to understand what the meaning of this one. So this means here, so tin in the alpha magnesium. So for example, we have, so let's assume this model. So let's assume this model. Assuming Z equal to 1, so it's a random mixing model. So this is the pure magnesium solid solution, alpha magnesium solid solution, HTP structure. So I take a magnesium HTP Gibbs energy from the my function and the mole fraction, and I have to take now tin Gibbs energy of HTP structure and the mole fraction. Okay, but unfortunately, the tin as HTP structure was not known at the time, so I actually changed it a little bit. So, for example, so let's assume we have this one, magnesium here, and then here tin. Okay, so this tin at the given temperature, the Gibbs energy here. So this is Gibbs energy, and you have the tin Gibbs energy, but this is solid tin, but this is not HCP structure. Okay, but now we have here magnesium solid, but this is in the HCP structure. So when you actually make the Gibbs energy function, you have to connect the Gibbs energy of HCP to the HCP. Okay, so HCP solution is connecting Gibbs energy of the HCP to HCP. So this should be tin under the HCP structure. And of course, you have the liquid magnesium, liquid tin, like this. So this is liquid, yeah. So this is Gibbs energy of liquid. This is Gibbs energy of tin. This is Gibbs energy of HCP solution. Okay. So I don't know this Gibbs energy. So I want to actually define this Gibbs energy somehow. So that's actually how I did it here. So that means I have this value. So I know this value from my database. Unfortunately, this value is not defined. Nobody defined before. Then I have to define by myself. If you cannot find this value in your own database, if your own, the compound database, then you have to actually create your own tin HCP Gibbs energy by yourself. Okay? So typically what we are doing is, okay, we know tin HCP. So the tin solid, which is very well known, this is actually BCT structure. And so let's assume I know this structure information and this Gibbs energy of this one. And I'm just simply adding certain amount of the positive value, make sure that this is metastable than this one all the time. Okay? And that is this value, 20.92920 kilojoule. So this is 20.92 kilojoule. This is huge. This is very unrealistic value, but at the time, I was a little bit stupid, so I just give the very big number here to make it very easily, to make actually the database much easily, okay? Okay, and then you are adding some access parameter to up and down, so that access parameter is this one, to make your shape of your HCP, okay? So then, I have to enter this Gibbs energy in my access parameter, my actual Gibbs energy equation. So here, when you enter this Gibbs energy GB, you have to enter Gibbs energy of this one. Yeah. So how can I do that? So here, if you come to the solution file again, so this is alpha solid solution I created already. So sublet is A, magnesium and tin. That's good. And remember Gibbs energy, magnesium, pure magnesium, HCP. And then tin, okay, I have this tin Gibbs energy from the BCT parameter from the function I have. So this tin here. So this can be taken from this function can be taken from your compound database directly. And then, so in order to find that actual additional parameter, I add this one plus 20.92 kilojoule times is the sharp joule. So sharp joule is actually the important. Okay, you have to enter something. The sharp joule should be defined. So here I add additional function by myself, and then say joule, and joule is 1 joule. Okay, so this value, joule is just naming. This is not real value. So this is actually real value. So definition of the joule is the 1 joule per mole in the the function here. And then if you go back again here, so this times 1 joule. So it means it's a 20,920 joule. Yeah, that's an additional value here. And that's exactly the same as this value. Okay, that's how you have to define. Okay, so sometimes you have to create your own function here to modify your Gibbs energy. Okay, and then the parameter, interaction parameter, this is the power 2, 1, and this one. So each model number 1, So model number 1, power 2, 1 with this value as it is. So I enter that value. Okay? So this is how I create this is how you can create your compound data. Actually the AlphaSource solution. Okay? Now, let's assume I have all this one, and then let me just save this one again. So save this one is magnesium tin solution, and then now let's go back. So you say you have difficulty to draw the sum of the figure I mentioned. So let's go back here. What kind of figure we need? So I think this is very easy. Say like you can do it very quickly. So that's no problem. And then figure number 2. So this is delta H of this plus this becomes this one. So where do you have to calculate this? You can do it in the reaction module. Yeah. In the reaction, you can enter this one as a starting. This species, 2 moles of this species, 1 mole of this species, and your product is this one, and you can set up all those things. And then in the calculation, you change the value of the temperature from about 300 degree Kelvin to the 1200 degree Kelvin, and then do the calculation. Then you can do the calculation. Okay? And you have to take, of course, magnesium and tin from the FT Light database or the compound database, and this one you have to create it by yourself. Okay? And then this one, where you have to do it. This is this minus this one. So this is initial condition. So some fixed temperature. So it means initial condition. And this is the changing with the temperature. And then this the difference between these two. So this can be calculated either in the reaction module, or you can do it in the equilibrium module too. So for example, if you want to do it in the equilibrium, so you can go here, equilibrium. So you can say, okay, I have Mg2Sn, okay, and you have to give the initial condition, yeah? So that's actually the important thing. You can give the initial condition. So let's say 980, I mean, whatever number you like. So from I'm just using the one default database here. So you can use your own database if you have it. And so here, and then do the next. And then you have to choose your own compound in this case. Which one? This one. You have to specify your compound because you are doing initial and the final. You know the both of them. So you know the initial one at certain temperature, final one without temperature, but what's the species you have to know already. And then say 980 to the 1200 degree Kelvin, every 10 degree, for example, like this. And then you can use the normal calculation, or you can use the normal and the transition. And if you take the normal and transition, then it will calculate every 10 degree. And then if there's phase transformation, it calculates exact transformation temperature as well. So you can have vertical shape. Okay. And then if you do the calculation, you can have this one. In this case, I'm sorry, there's one more thing. You have to be careful here. So one more thing I have to actually mention here is you are taking this one, and then this is actually liquid part. This is liquid part. This is solid and this is liquid. So when you do the calculation up to here, you are solid is necessary here. Above this one, you need the liquid phase. And liquid phase, we don't have it in the compound database. Liquid phase is inside of your liquid solution here. Okay? So let's assume this is your own database. Then you have to take your own database to solid and the liquid, and then do the calculation. Then you can see the key. And then plot output, plot the result. And what we are plotting, so axis, y-axis should be your delta H. Okay? And x-axis should be your temperature. And then refresh, then it will actually adjust your coordinate, and then say okay, and then plot. Then you have like this. Okay? So this is and also the input, I mean, depending on your amount, mg2sn 1 mole or mg 0.66, tin 0.33, or I mean, depending on, or 1 gram of mg2sn or 1 mole of mg2sn. Okay, so depending on that, the value could be different. Yeah. So in this case, it's 1 mole of kilojoule per mole, 1 mole of mg2sn based calculation. Okay, this is how we can do. This is same thing, enthalpy of mixing at each given temperature. So you have to select only liquid phase from the two starting points. Okay, so enthalpy of mixing for the liquid phase. So it means now I have to go here. So I say magnesium and the tin at the given temperature. So you have to select your database starting point as the liquid phase, for example, 1000 Kelvin. And then tin also, you have to choose your database liquid and the 1000 Kelvin. And then you can say that 1 minus A and the A as a variable. Yeah. So whenever you have the variable, you have to use this kind of the bracket, the open bracket and the closed bracket, and you have the variable. And then initial condition, this is important. You have to set the initial condition with the liquid and the same temperature, 1000. And then next, I don't need anything else. In this case, I need only liquid phase, and then 10,000. And then from value from 0 to 1, 0.01, for example. Okay. If you have the solid and liquid together, if you want to see the whole picture, then you can select all the phase, all the possible phase as well. But in this case, I want to see only liquid part, then I can do it in this way. Then once you do it, again, you go to the output, plot result, and what you have to plot is axis, y-axis is delta H, because I'm plotting the H. X-axis is now the composition. So composition in this case is alpha. A is alpha in the factory. It's a variable. So alpha is changing from 0 to 1. That's the same as the amount of the tin, mole fraction of tin in this case. And say OK, and then plot. Then I'm switch. The axis was not adjusted enough. So go again, replace it, refresh, and say OK, and then plot. And you can get this one. Why? This is positive. This is positive than 0. Yeah? I'm sorry, why is right there? Let me go back again. So 1000, FT light. So magnesium tin and liquid, yeah. 0 to 1, 1000 Kelvin. Yep, let's go again. Something strange. And then, so it should be H equal to should be 0. Why is not 0? This is when A equal to 0, so it means pure magnesium liquid FT light. Magnesium liquid, this magnesium liquid, it should be 0. Why is not 0? Am I doing something wrong? It's strange. Have I changed something? Initial condition, yeah. So 0, 1000 Kelvin. It should be. It's very strange. Let me check again. So now actually coming out okay. Just a second. Because even there's no actually solid phase, no liquid compound. It's a pure liquid. So liquid, and it was this value, almost 0. Yeah. It's basically 0. And we set slightly different way. If I remove it, it's 0. I'm sorry. So it's a 3 point something 10 to the minus 5. So it's nearly 0. So it's okay. We set slightly different value. to make sure that your liquid solution is more stable than your pure liquid magnesium. So that's the reason. And then there was some problem in the other side. So here actually is the problem. Liquid tin, and then minus tin equal to 1, 0, tin liquid, and tin liquid. This is different. Very strange. Let me just try again in this way. Probably we used FPS. This is now almost 0. I have to check this one. This is very strange. Typically it should be 0. So that means the database actually using the different, actually the tin pure Gibbs energy. So the Gibbs energy is different. That's why it's different. Okay. Very weird. I don't know why it was set in this way. Anyway, so if you do it, then you can plot the result. So again, and axis, refresh, and plot. Then you can get actually the Gibbs energy curve. Okay. And then you have to do the multiple calculation like this. And then after that, you have to click this one, superimpose. Then you can actually put the one figure to the other one. And into actually the one, actually the, and so you can make one figure in the end. Okay. That's possible. And then third one, this one, activity is same thing. So when you do the calculation like this, basically, so you have two choices. So you can either enter the pure liquid here, or in this case, it's liquid. So activity of what? That's important. Activity of the liquid magnesium standard state. So tin standard state, tin liquid standard state. So this is very important one. So if you do it, so typically when you go to the output, plot result, and here in the axis, and now you have to say y variable as activity. So activity here. And then x-axis is alpha, that's okay. And then say okay. So when you say activity, you have to define which activity you are talking about. What kind of component activity. Then you can go select. So activity of what? So I want to have activity of liquid magnesium and liquid tin. Okay. If you want to have the activity of the magnesium solid, then you have to select the solid phase and then click that solid phase. Basically. Then you can have activity of solid phase. Okay? And say okay, and then plot. Then you can have magnesium and the tin activity in this way. Is it okay? Good. So this is how you can use it. Okay? So this is, I think, everything I want to show you today. So I show you how to create now really ternary solution data. I didn't upload ternary solution database, but you know how to actually create ternary solution database. And so I really